Salam and welcome everyone. So today I am just compiling a bunch of shorter videos from my channel for any student who is reviewing your physical chemistry for an exam or for a test. The goal of this video is for you to review the examples that I've done already on this channel from the physical chemistry Atkins textbook. It is to help you in your journey through physical chemistry, whether you're about to take a test or whether you're doing a bunch of problem set. I wish you guys all the very best. Please enjoy the video. So today we're going to be working on the question on the screen that says when 178 joules of energy is supplied as heat at constant pressure to 1.90 mole of gas molecules, the temperature of the sample increases by 1.78 kelvins. Calculate the molar heat capacities of the gas at constant pressure and constant volume. So the first thing you note is we're going to reread the question and jot things down. So we're told that when 178 joules of energy is supplied as heat, so this means that Q equals 178 joules at constant pressure. So Q sub P, since it's constant pressure, to 1.9 mole of gas molecules. So the number of moles is 1.9 mole. The temperature of the sample is increased or increases by 1.78 Kelvin. So change in temperature equals 1.78 kelvins. Calculate the molar heat capacity of the gas at constant pressure. So that would be Cp, comma M, okay? And then Cv, comma M. And we're asked to calculate the molar heat capacity of the gas at constant pressure and constant volume. So Cp, comma M is the molar heat capacity at constant pressure, and Cv, comma M is the molar heat capacity at constant volume. So the first thing you need to know is because we're given what the heat is at constant pressure, like at the beginning of the first like sentence, you would actually use this information to you are going to use the information to be able to determine the formula that we're supposed to use. So Q heat at constant pressure is actually equal to the number of moles times the molar heat capacity at constant pressure times the change in temperature. So from this, we can determine what the molar heat capacity is at constant pressure. So CPM equals, we're going to put this equation up top here in terms of Cp, comma M. So that's going to be Q or QP divided by number of moles times change in temperature. So this is how you solve for the molar heat capacity at constant pressure. We already thankfully have the heat at constant pressure to be 178. We have the number of moles and we have the change in temperature. So all we have to do now is just simply substitute. So you have Cp, comma M equals, the heat is actually 178 joules. So that would be 178 joules divided by the number of moles. So that's 1.9 mole times change in temperature will be 1.78 kelvins. So when you have all of this information, you end up having 52.6316. 52.6316 joule per mole Kelvin. So yeah, remember now that whenever you're dealing with chemistry, you're supposed to like round up and you're supposed to look at the sig figs that you're given and you're supposed to basically approximate to the sig figs that you're given. So, or to the lowest sig figs that you're given. So in our question, we have 3 sig figs for heat, we have 2 sig figs for number of moles. So we're going to approximate whatever our answer is to 2 sig figs. So Cp, comma M ends up being Cp, comma M ends up being 53 joule per mole Kelvin. So this is basically the answer to this question. So to find Cv, comma M, there's a formula that we're supposed to use, right? We have this. Now, the formula does not come in molar heat capacity, but instead it just comes at heat capacity. So the formula is Cp minus Cv equals Nr, where Cp here is the heat capacity at constant pressure, okay? Cv is the heat capacity at constant volume. So yeah, that's basically it. The next thing you have to do is for you to determine how do you go from heat capacity to molar heat capacity. So For you to go from CP, comma M to, sorry, for you to go from CP to CP, comma M, and for you to go to from CV to CV, comma M, all you have to do it is CP divided by number of moles equals CP, comma M, as well as CV divided by number of moles is equal to CV, comma M. So the molar heat capacity at constant pressure is equal to the heat capacity divided by the number of moles, and the molar heat capacity at constant volume is equal to the heat capacity divided by the number of moles. So that's it. So CVM is equal to the heat capacity divided by number of moles. So that's how you do it. So from this information now, we can go on to solve this question. Since we're just giving heat capacity, what this is telling us is that we can just divide all of this information, because whatever you do on the left side, you have to do on the right side. You divide it by the number of moles. So you divide it, and of course you divide number of moles here, number of moles. So what you end up with is CP, comma M minus CV, comma M equals R. So this is it. Now we've already determined what CPM is. We know what R is. R is just the regular gas constant. So that's 8.3145 joules per mole Kelvin. So CV, comma M, you just rewrite in the equation. What you actually have is CV, comma M equals CP, comma M minus R. So now we know what CP, comma M is. We just solve for it. We know what R is. We have that to be a constant. So CV, comma M equals CP, comma M is actually 53 joules per mole Kelvin. But in chemistry, when you are using an information to do further calculation, you have to leave it in the actual value, not the approximate value. So hence, we cannot use 53 joules per mole. Instead, what we can use is 52.6316, because we want to use the actual value to do further calculation, because if we use the approximate value, we're not going to be getting the actual value. So what we need to do is use the actual value, and then at the end of the calculation, then we can approximate the new value that we're going to get. You're going to see what I'll do in a second. So that will be 52.6316 joule per mole Kelvin minus 8.3145 joule per mole Kelvin. So you subtract this calculator. So you have CV, comma M to be 44.317 joule per mole Kelvin. So approximately CV, comma M is approximately 44 joule per mole Kelvin. So this is actually the value that we're going to approximate. And you may be confused that how do we get 44? Well, let's not forget our question. The smallest value that we're given in the question is a two-sig fix. So we have to put our information and estimate or approximate to two-sig fix, and we have 44 joules per mole Kelvin. So if you have any questions or suggestions, please put it in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, when 229 joules of energy is supplied as heat at constant pressure to 3.0 mole of argon gas, comma, the temperature of the sample increases by 2.55 kelvins. Calculate the molar heat capacities of the gas at constant pressure and constant volume. So they told us energy supplied as heat. So basically Q here is equal to 229 joules. And this situation occurs at constant pressure to 3.0 moles. So the number of moles we've been told is 3.0 mole. And the temperature of the sample increases by 2.55 Kelvin. So they are telling us now that change in temperature is 2.55 kelvins. We're asked to calculate the molar heat capacities at constant pressure. So C, P, comma M. So that's the molar heat capacity at constant pressure is this. So we're asked to calculate that, as well as the molar heat capacity at constant volume. So CVM is that. So basically, that's just what we're asked to do. Well, the first thing you have to remember is this. So as you can see, I have boxed the constant pressure. And since we're asked to find CPM as well as CVM, you have to be able to understand the question and break it down in your mind, and also write things down so that you would not be confused. So generally, the formula for heat at constant pressure is Q sub P equals number of moles, okay, times Cp, comma M, times change in temperature. So this is basically it. Now we have the heat at constant pressure, okay, we have the number of moles and we have the change in temperature. So we can rewrite the formula in terms of CPM. So molar heat capacity molar heat capacity at constant pressure equals QP, okay, heat at constant pressure divided by the number of moles times the change in temperature. So this is basically what we're now going to use to solve it. So remember, heat at constant pressure, when we look back at our question, is 229 joules, okay. The number of moles is 3.0 mole, and the change in temperature is 2.55 kelvins. So now what you have to do is for you to basically multiply and work with what you have. So what you end up with is putting this information in the calculator. We end up with 29.9346 joule per mole Kelvin. So this is the molar heat capacity at constant pressure. Now you have to go back to the question that we're given because we're told to find the molar heat capacity at constant pressure. You see that the information we're given the heat, the value for heat as 3 sig figs, and we're also given the value for number of moles as 2 sig figs. So we have to go with the lesser sig figs in chemistry. Don't forget to always put your information in number of sig figs that you are expected to do whenever you're doing science or math related problems. So you have CPM equals 30 joule per mole Kelvin. So this is basically how you solve this question. Now you may be thinking, okay, how do we solve the molar heat capacity at constant volume? Because we're given that as well. But good thing about it is that there is this formula that works for this perfectly. So this formula is just called CP minus CV equals NR, where CP is heat capacity at constant pressure. So this is heat capacity at constant pressure, right? As well as CV is heat capacity at constant volume. So these are the two. So now you're going to be thinking, okay, they told us the molar heat capacity, not just the heat capacity. So one thing you can do is note that CPM is the same thing as the heat capacity divided by, sorry, the heat capacity for pressure divided by number of moles, and C comma Vm here is the heat capacity at constant volume divided by the number of moles. So you can literally rewrite this formula and work with this. So note that if there's heat capacity, to go from heat capacity to molar heat capacity, you have to divide by number of moles. So if you're giving heat capacity and you're trying to go to number of if you're giving heat capacity and you're trying to go to molar heat capacity, you just have to divide by number of moles. If you're giving molar heat capacity and you're trying to go to heat capacity, you're just going to multiply by the number of moles. So this is just like a simple math. So now let me erase this and continue our work. So we're now trying to go from heat capacity to molar heat capacity. So we're going to divide this by number of moles, divided by number of moles, divided by number of moles. So whatever we do on the left side of the equation, we do at the right side of the equation. So cancel out number of moles. So what we end up with is Cp comma M minus Cv comma M equals R. So that's basically it. So we have 30 joules per mole Kelvin. We have the value for R to be 8.3145 joule per mole Kelvin. So basically, CVM ends up being, rewriting the formula, you have Cp comma M minus R. So this is basically the information. So yeah, we just substitute. So you have Cv comma M equals CPM. That will be 30 joules per mole Kelvin. You can do that, but let's not forget that we're doing science. We can't just say 30. We have to go back to the actual value we got before we did the 3 sig figs, so that when we're solving it, we get the exact value. So we actually have to use 29.9346 in this particular question. So that's how you do like science related problem. You're not going to use the approximate value to do a new calculation. You're going to use the actual value, and then whenever you're done with the new calculation, then you're going to approximate. So we're going to do it right now. So you have 29.9346 joule per mole Kelvin minus 8.3145 joule per mole Kelvin. So CV comma M is the same thing as 21.7896. So 21.7896 joule per mole Kelvin. So rewriting CV, comma M, we have approximately 22 joules per mole Kelvin. So this is the answer for CVM. You can see that we solve for CPM, and we immediately could solve for CVM using this particular formula. So this is basically how you do this question. If you have any questions, put it in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, when standard enthalpy of formation of ethyl benzene is negative 12.5 kilojoule per mole, calculate the standard enthalpy of combustion. So the first thing you have to do is the standard enthalpy of formation of ethyl benzene is this. We're told the standard enthalpy of ethyl benzene. So we're just going to say ethyl benzene is EB for now. So that would be standard enthalpy of formation. So like this, okay, of ethyl benzene. So EB is going to be equal to negative 12.5 kilojoule per mole. Now we're asked to calculate the standard enthalpy of combustion. Now, one thing you have to note is that in a combustion reaction, this is a reaction that occurs whenever a molecule is reacted with oxygen. So this was taught to you in your Gen Chem classes, and now you know that information that you're going to apply to this PChem course. So ethyl benzene is actually of the structure, even though the structure is not exactly what we need in this question, is just going to be something that will help you anytime you're not given the actual structure or molecular formula, right? If you're not given the molecular formula, you can draw out the structure to determine whatever this is. So this is ethyl benzene. You have the benzene group right here, and then you have the ethyl group. Sorry, you have the ethyl group right here. So that's how it is. So yeah, you have the ethyl group right here, and then you have the benzene group right here. So this is basically ethyl benzene. So some of you may be wondering, why am I like being too like why am I like talking about every single thing like very intensely? It's because I want everyone to be able to be on the same page, because you need to be able to get every single part of this information in order for you to do well. So yeah, so we're gonna count now how many carbons and how many hydrogens we have, so that we'd be able to do the reaction. So you have one carbon, two carbon, three, four, five, six, seven, eight. So you end up with C8. Then we'll have to determine how many hydrogens. We know we've got two here. So this is CH2, we have CH3. So this place has five hydrogens. This place has no hydrogen because there are four bonds. So that would be one hydrogen here, another hydrogen here, third, fourth, and fifth. So five hydrogens plus the five hydrogens in ethyl group is going to give you 10 hydrogens. So you have C8H10. So rewriting this, we have C8H10 plus the combustion reaction, because we're asked to find the standard enthalpy of combustion for the reaction. So this one here, or the standard enthalpy of combustion, basically, yeah, for this particular reaction. So we're supposed to naturally, anytime you have a combustion reaction, you're supposed to always have carbon dioxide, CO2 gas, as well as H2O and water, which is in liquid form. So this ethyl benzene is a liquid, and of course oxygen gas is a gas. So now we're going to balance this chemical equation, because that's the next thing you have to do. So you can see that we're each inching into the question, right? Calculate the standard enthalpy of combustion. So now we're going to balance this equation. So you have eight carbons here. We have one carbon here. In order for us to balance it right, we're going to put an eight here. So now we have the carbons are balanced. We have oxygen here. 2 times 8 is 16. So we have the balanced carbon here, but we have then 16 oxygens here. And then we have how many hydrogens here? We have two hydrogens here. We have 10 hydrogens here. Well, 10 hydrogens and 2 here. In order for us to balance it, we know that 10 divided by 2 is 5. So we're going to put 5 here. So now we've balanced the hydrogen. So now we have the 10 here. And of course, we have the 10 here. So now the only thing that remains for us to properly balance, in order for us to have a balanced chemical equation, is actually oxygen, because we're done with carbon, we're done with hydrogen. And both left and right side of the equation have the exact number of atoms. So next we have to determine the number of oxygens we have on both sides. We can see that on this side we only have two oxygens. On the left side we have two oxygens, right? And then on the right side we have eight 8 times 2 is 16. So we have 16 oxygens, and then we have 4 CO2, and then we have um 5 oxygens in the H2O. So that's 5. So making a total of 21. And then we have 2. How do we go from 2 to 21? Well, 21 divided by 2 is the same thing as 10.5. So we have 10.5 here, or we can just say 21 divided by 2. So when you look at all of this information, you would see that everything is balanced, right? We have a total of 8 carbons on both sides. We have a total of 10 hydrogens on both sides, and we have a total of 21 oxygens on both sides. So 21 divided by 2, this 2 you can think about it like you're canceling out, or you can just say 10.5 times 2, which is 21. So that will be 21 oxygens on both sides, right? And then this one, you have 16 plus 5. So that's a total of 21 oxygens on both sides, right? So that's it. So now we're just going to rewrite this equation. So that's basically our work. Since the combustion reaction is a reaction, you can just have, or since combustion is a reaction, you can have the change in enthalpy of combustion to equal this formula here. And I'm going to explain the formula to you. So you have this, and then you have the change in enthalpy of formation, okay, or change in standard enthalpy of formation minus this here as well. We're just going to write the same thing. But then you may be wondering, well, why are we writing the exact same thing? Well, this one is for products, okay, and this one is for the reactants. And this V here is just the stoichiometric value, meaning the coefficient or the stoichiometric coefficient. So this V here is going to be whatever is in front of the molecule. So if you have 2O2, this V here is going to be the stoichiometric coefficient of oxygen gas of O2, which in this case is 2. I'm just basically showing you what's going on here. So now we're just going to rewrite everything that we have. I'm going to break it down. We know now that we're gonna sum up the standard enthalpy of formation of the product, and we subtract it from the standard enthalpy of the reactant. So this is what this is going to look like now. So we have this here equals 8 standard enthalpy of formation times CO2 gas plus 5 times standard enthalpy of formation of O2 gas, or H2O gas, sorry, H2O liquid. Why am I saying H2O gas? H2O liquid. So I'm just showing you what we're doing here. So you can see now that this first part of the information involved just the product. So the right side of the equation, the CO2, we have the coefficient at the front, and then the standard enthalpy of formation of just the CO2, while we brought the coefficient of CO2 to the front, and then plus we brought out the coefficient of H2O to the front, multiplied by standard enthalpy of formation. So basically, this is how you put down the structure of the information. Then you say minus, we're going to do the one for the reactants. So that would be enthalpy of formation of C8H10, okay, liquid, plus 21 over 2 is going to be brought forward. And then, of course, standard enthalpy of formation of O2 gas. So this is basically how it's done. This is how you structure or write out the structure of this part. Is very, if not the most important part of the question. So let's not forget that we've been given the standard enthalpy of formation for ethylbenzene. So this is the whole point. This is the reason why we have this. So let me rewrite the standard enthalpy of formation of ethylbenzene. So that would be that we had for EB here is the same thing as the standard enthalpy. If you look at your question again of C8H10, okay, liquid. So all of that information is negative 12.5 kilojoule per mole. I'm just rewriting it so that on this part of the question, you'll be able to know what you're doing. So yeah, so now let's go on to input the information and to substitute. We know now that 8 times the standard enthalpy of formation of CO2 gas. Some of you may be wondering, well, they only gave us the one for ethylbenzene. They did not give us the one for oxygen. They did not give us the one for H2O. They did not give us the one for CO2. Many times when you have questions like this, there's going to be a resource section of your textbook that has all of this information. So right now, they didn't give us the standard enthalpy for CO2. So if you're doing an assignment, you have to go to the resource section of your book and determine what the standard enthalpy of formation for CO2 is, and for H2O and for O2. They would not give it to you if it's an assignment. Maybe in a test or an exam, they're going to give you all the values for you to do it. Or maybe there's going to be a resource section for the quiz or for the exam. But just note that you can find this information on Google, or you can find it in the resource section of your textbook. Looking at textbook, I see that standard enthalpy of formation for CO2 is negative 393.51 kilojoule per mole. So I'm substituting. This is where I am right now. Okay, that is the standard enthalpy of formation for CO2 gas, plus 5 times the standard enthalpy of H2O gas. I'm right here now. So make sure you follow this, the resource section of your book. I'm purposely not writing it out separately for you guys because I want you guys to be actively searching for it as well. Because in an exam or in an assignment, you're not going to have me here writing out the information for you. So you have H2O, the standard enthalpy of formation. Looking at the research section of my textbook, I see that to be negative 285.83 kilojoule per mole. Okay, so that's that. And then that is the information here, minus the standard enthalpy for ethylbenzene. We're given this one, luckily, is just negative 12.5 kilojoule per mole. And then plus 21 over 2 times the standard enthalpy of formation for O2 gas. Looking at our information, we see that that is just simply zero, meaning everything right here is just zero. So of course, you input your information in your calculator. You have 8 times negative 393.51. We have that to be negative 3148.08 kilojoule per mole. Okay, minus negative 1429.105 kilojoule per mole, plus 12.5 kilojoule per mole. So yeah, all of this information right here would be standard enthalpy of combustion is going to equal negative 3148.08 minus negative 1429.15 kilojoule per mole will actually give you and all of that information plus 12.5 kilojoule per mole. So when you put all of this information in calculator, you end up getting negative 4564.73 kilojoule per mole. And as you can see, this information is in one decimal place. So you can just put this here and you can say the enthalpy of combustion that you're asked to solve is, and so yeah, standard enthalpy of combustion is negative 4564.7 kilojoule per mole in one decimal place. That is the answer to this question. Or you may be asked to solve this based on the fact that this is 12.5 kilojoule per mole in the question given to you, and that's 3 sig figs. You can also say the answer could be, depending on what you're asked to do, it could be in 3 sig figs, it could be in decimal places, whatever you're asked to do. So that would be negative, in 3 sig figs, that would be negative 4.56 times 10 raised to the power of 3 kilojoule per mole. And this is just basically the answer. I wish you guys all the very best. If you have any questions, please leave it in the comment section. And I wish you guys all the very best. Assalamu alaikum warahmatullahi wabarakatuh. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, for tetrachloromethane, the change in enthalpy of vaporization is equal to 30.0 kilojoule per mole. Calculate heat, work, change in enthalpy, as well as change in internal energy when 0.75 mole of tetrachloromethane is vaporized at 250 kelvins and 1 bar. The first thing you need to know is this. We've been given a question where we're told to determine heat as well as enthalpy in the same question. We have to understand that at constant pressure, heat is equivalent to the change in enthalpy. And we see that in this particular question, they did not tell us that the pressure was increased, it was decreased. They did not say the initial state was a particular number and then the final state was a particular number. They just told us that it's happening at 1 bar. So we can assume from this question that the pressure is constant. And because the pressure is constant, the heat as well as enthalpy will give us the same value. So what I'm trying to say is when we find heat, right, and we find enthalpy, we can simply, sorry, when we find heat or we find enthalpy, we can just simply know that finding one would equal the other. So that's basically what this is saying. Now, we're also told to find out work as well as change in internal energy. Note that by the time we determine the value for work, all we have to do is just remember that the change in internal energy is just Q plus W. So whatever the value for W is will be added to whatever we've solved for heat, and we will get the answer. So I just want to talk about the fact that this question should not scare anybody because it's a very fundamental question, and remembering the formulas that we've been using since we started this particular topic in physical chemistry is going to be the same thing you're going to be doing. So now, the only value we're given, right, um, aside from temperature and pressure, is the number of moles. So the values we're given aside from them are the number of moles as well as the change in enthalpy for vaporization. So the first thing you have to do is this. Remember that the units for heat as well as work is joules. So the units for heat, the unit for change in enthalpy, they are all joules. Okay, just joules. And this particular change in heat for vaporization is in kilojoule per mole. So what this is telling you is that enthalpy, okay, is just simply the change in vaporization for enthalpy times the number of moles. So this is what this is going to show you here. I'm just going to do the equation, and I'm only like breaking this down because I don't want a situation where people will be confused because they may be wondering like, okay, how did they go from here to here? So what I'm saying is the change in enthalpy is equal to the number of moles times the change in enthalpy of vaporization. Because if you remember, the unit for enthalpy or change in enthalpy is joules or kilojoules, okay? And then here is just simply the unit for change in enthalpy for vaporization is kilojoule per mole. So to go from the information on the left to the right, you have to use the number of moles. Or to go from the equation from the right to the left, you also have to use the number of moles. So in this particular question, we're just going to be multiplying the number of moles times the change in enthalpy for vaporization to get the change in enthalpy. So that's just how we're going to do. We're going to math it out. There's no major formula to go from changing enthalpy to changing enthalpy of vaporization. Just use the number of moles. So writing that out, we have changing enthalpy, which we're supposed to solve, is just the number of moles, which we've been told is 0.75 moles. Okay, remember that's what the question said, times the change in enthalpy for vaporization. So times 30.0 kilojoule per mole. So of course you cancel out the mole. So that would be 22.5 kilojoule. So that is basically the value or answer to enthalpy. And let's not forget, heat at constant pressure as well as change in enthalpy are the same value. So heat is therefore also going to be 22.5 kilojoule per mole. So yeah, that's basically what you do. If you want to stick to, yeah, that's basically what you do. That's 100% what you do. So we're going to stick to kilojoule per mole. We're not going to change it back to joules per mole. It doesn't really matter. That's just basically what we have. So the next thing we have to do is for us to determine work. Remember that generally the formula for work is negative P external or pressure, okay, that we're dealing with times change in volume. But we also have to remember the chemistry behind this particular question. We're told that tetrachloromethane vaporized to go from liquid to vapor is gonna be basically a chemical reaction. So what I'm trying to say is to go from maybe having something in a container which is in liquid form, okay, to gaseous form is going to look like this. Everything vaporized. So maybe if there's a hood in the lab, you see the volume goes from whatever is in this liquid to everywhere. You can see that the volume is going to significantly increase as it's basically vaporizing. So it's going to go everywhere. It's just like how water can be small in a pot, but when you heat it so much and it starts to vaporize, the entire room feels steamy. That's because the volume of water has left the water has left has vaporized from the pot to everywhere in the room, and you can see the volume increases. This is the reason why you feel the steam all over, even though it might just be a small portion of water. So what this is telling you is this: that since you have this information, you cannot look at volume in the same way anymore, because the volume of the gas, right, has become significantly greater, right? Significantly, like much, much larger than the volume of the liquid. So than the initial volume. So the final volume of the gas is significantly greater than the initial volume of the gas. So knowing this information, we understand that the final volume is going to be approximately the change in volume. It's just like, say, the volume of the gas before, sorry, the volume of the liquid before, say, initial volume was 5 milliliter. And then all of a sudden it goes from 5 milliliter to a million, okay, milliliter. Well, if you want to do the math, you would see that the final volume, which is here, would be significantly, meaning 1 million millimeter is significantly greater than 5 milliliter. So, what this is trying to tell you is that approximately the final volume is the change in volume, and we can represent this mathematically as rewriting, basically rewriting the equation. So, we end up having work done equals negative P times V final. So, this is basically what we end up with. So that's going to be the one that we're using. Now, we go back to our question. We remember that we're given pressure, right? 1 bar, but we were not in any way, shape, or form given the final volume. So we remember that the common formula that we started when we started with PChem is PV equals nRT. So since we don't know what the volume is, because we're not given the initial or final volume or any volume, we can find whatever the value of VF is, but in terms of other parameters. So that means V here is now going to be nRT divided by P. So basically that's just going to be what we're going to input. So rather than having W equals negative P VF, we're gonna have W equals negative P, so times nRT divided by P. Well, the pressure remains constant, the same value, so we can just simply cancel that out. So pressure cancel. So really work done ends up becoming W equals negative nRT. So what else are we going to do? We're just going to substitute. So W equals negative, what is the number of moles that we're given again? 0.70. Sorry, 0.75. So 0.75 mole. We've been told the number of moles. Sorry, the gas constant. We've been told the number of moles. So next we move on to the gas constant. So that will be 8.3145 joule per mole. Kelvin, and we've been told the temperature. If we go back to the question, we see temperature is 250 kelvins. Okay, so 250 kelvins. So of course, we do the math, cancel out of the units first, cancel out the Kelvin, the number of moles, and we just multiply. So that will be W equals negative 0.75 times 8.31415, right, times 250, all of that joules. So W equals negative 1558.969 joules. So that's basically what's going to be the answer right here. So of course, because we want to clean up our work, we can just do this in kilojoules, right? We can also determine the value in kilojoules. So that's going to be W equals negative 1.55897 kilojoule. So that's how you do it. Now, let's not forget that the change in internal energy, which is the last thing we're asked to solve for, is Q plus W. So going back to the question, you see that we're also asked to determine the change in internal energy. So we know that's Q plus W. We already know the value of our Q, which is simply 22.5 kilojoule per mole, as well as the value of our work. So we're just going to substitute. So you have change in internal energy equals 22.5 kilojoule, okay, plus minus negative 1.55897 kilojoule. So when you do this information, we end up getting 20.94103 kilojoule. So of course, we're given our initial question. We're given 3 sig figs for the change in enthalpy of vaporization. We're given 3 sig figs for number of moles and 3 sig figs for the value of temperature, and we use all of that information. So we have to put our final answer in three sig figs. So the change in internal energy becomes 20.9 kilojoules. So this is basically the answer to this question. So hopefully I've been able to break down this information in a way that you're going to understand. There's also another video that is going to be posted on my channel for another question using the same information and same format. So make sure you watch that video as well. If you have any questions, please put it in the comment section. Today we're going to be doing a question on the screen that says a sample containing or consisting of 1.0 mole of perfect gas atoms, for which CVM, which is the molar heat capacity, equals 3 over 2 of the gas constant, hence 3 over 2 R, initially at P initial equals 1.00 atmospheres, and also T initial, meaning the initial temperature is 300 kelvins, is heated reversibly to 300 Kelvin at constant volume. Calculate the final pressure, the change in energy, the heat, and the work done. So the first thing you have to do when you're working with a question like this is for you to, first of all, write out the parameters. We're told that we have 1 mole of the perfect gas. So the number of moles is 1.00 mole. We know that the molar heat capacity, CVM, equals 3 over 2R. We know that the initial pressure, so P initial, where it's here, it's denoted P1. You can also say that P1, P2, or PI, PF. So P initial, P final. That's what I'm going to be using in this particular question. So that one is 1.00 atmospheres. And the temperature, the initial temperature, is 300 kelvins. Now, we're told that this is just like the beginning of the reaction, but there is increase in temperature. So basically, the sample is heated reversibly. So that means the final temperature, because there's heat applied, is going to be more. So, and we're told that that is 400 kelvins. And then all of this occurs at constant volume. So the first thing you have to know is this. We're asked to find the final pressure. But before we do that, we can determine some information from this question. You see, we're told that this is happening at constant volume, and usually the general formula for work is negative P change in V. Well, because this is occurring at constant volume and the volume is the same all through the entire process, the entire reversible process, well, since there is no expansion, there's no change in volume, what you're going to end up with is a zero, because the change in volume is zero. I'm sorry, the constant volume will make the change in volume zero. The work is going to be equal to zero. So that's one thing I need you guys to know. So we've gotten the answer to one of the question. But then we have to remember that we have internal energy change in U is usually equal to Q plus W. So the change in internal energy is heat plus work. We already know that work is going to zero or is equivalent to zero. Hence, the internal energy change in U is going to be equal to just heat by itself. So I wanted you guys to know that. So now we have successfully answered one question, which is W. So when we determine what the value for heat is, we're going to also note that that value is equal to the change in internal energy. But before we go on to solve for heat, we can work on this question, right? Because we're asked to find the final pressure. Well, since this is an initial volume, sorry, this is an initial pressure, final pressure type of question, we remember that first of all, the ideal gas equation is PV equals nRT, right? And N, so number of moles is constant, gas constant is constant, and volume is constant. The only things that have a change in value, meaning the initial and the final have different values, and the initial and the final is basically not the same, is the pressure and the temperature. Hence why we have an initial pressure and a final pressure, and an initial temperature and a final temperature. So what we're going to do is that we're going to put PT in one side of the equation and put the constant information on the other side of the equation. So when we do that, what we end up with is P divided by T equals NR divided by V. So if you do your math very well, this is what you're going to get. All this information is constant. And you're going to see the reason why I'm writing this down step by step. So all of this information is constant. You're wondering, okay, what is the point of this? Well, the point of this is because we know it's constant, meaning every single time, every single moment in this entire process, the NR divided by V is going to have a constant value. Hence, the initial, so P initial divided by T initial is going to have the NRT constant, this entire thing to be constant, and
P final divided by T final is going to have nRT as a constant information. So what we can do now is to merge two of them together. So we end up with P initial divided by T initial equals P final divided by T final. So P final divided by T final. So this is what we are going to actually use to solve the question. So all we have to do is just input the information. We have the P initial. We're told that that is 1.00 atmospheres. So we can just say 1.00 atmospheres divided by T initial. So initial temperature is 300 kelvins. And then P final here divided by T final. So the final temperature. So that's the final temperature, which is 400 Kelvin. So yeah, that is what's going on here. So one thing we can do is we can just simply cancel out Kelvin since we're actually solving for P final. And when we do P final here, we can just simply cross multiply this, and what to end up with would be 1.00 atmospheres times 400, okay, divided by 300. So basically we cross multiplied and we did the information in terms of just PF. So when we do that, of course, we cancel out this. So this will be 4 here, this will be 3, and that will be P final is going to just simply equal it's going to just equal 4 over 3 atmospheres, which is the same thing as 1.333 atmospheres. But then let's go back to the question in order for us to see how many sig figs. 1.0 is 3 figs, sig figs. 1.00 atmospheres, 3 figs, 6 figs. 300 and 400 kelvins are also in 3 sig figs. So we're just going to put this answer in terms of 3 sig figs. So P final is actually going to be 1.33 atmospheres, and that is basically the answer to this question. So the next part of this question is that we're supposed to determine heat, right? Before we do that, let's not forget that heat is the same thing as change in U, because of course work is equal to 0. So what this is telling us now is that we're going to determine heat. So that would be heat at constant volume is equal to CV, comma M times number of moles times the change in temperature, right? Times the change in temperature. So times the number of moles times the change in temperature. So this is basically the formula that we're working on right now. Sorry, not that we're working on, that we're working with right now. So the molar heat capacity times the number of moles times the change in temperature is going to give us what the heat is at constant volume. So all we have to do now is to just input all of the information into the equation. We know that according to the question, the molar heat capacity is 3 over 2 of the gas constant. And the gas constant, by the way, is denoted as R. And the gas constant for this particular question, don't forget that the unit for heat is in joules, right? So that's just basically 8.3145 joules, right? Per mole Kelvin. So that is what the gas constant is. Since we're dealing with the CVN, and that is telling us that this is equal to 3 over 2R. So we're just going to say 3 over 2R, which we're going to input here as 8.3145 joule per mole Kelvin, okay, times the number of moles that we're given, which is 1.00 mole, okay, times the change in temperature. And we know that the initial temperature is 300 Kelvin and the final temperature is 400 Kelvin. So that's TF minus T final minus T initial. So that would be 400 Kelvin minus 300 Kelvin. So this is basically how you do this question. So QV here is just going to be 3 over 2 times 8.3145. But before we go there, let's start canceling out the units. Let's cancel out the moles. Let's cancel out, we can't cancel anything out again because we need to subtract 300, from 400. But let's just work with what we have for now. We have 3 over 2 times 8.3145. So we have 3 over 2 times 8.3145. So that would be 12.4718 joule Kelvin, okay, times 1.0 times 400 minus 300. So that would be 100 Kelvin. So you cancel out the kelvins and you see that 12.47175 times 100 equals 1247.18 joules. So this is basically the answer that we are getting. But the issue is that we cannot put this in chemistry, mainly because we have to put things in the number of significant figures that is proper. So we're going to go back and see how many sig figs is in this question, just like we did for the final pressure solution. We see that it's three sig figs that we're supposed to use. So we're just going to answer this question up until three sig figs. So that would make this the heat at constant volume to be 1.24, but then we have the 7 here, so we're going to approximate. So that'll be 1.25 times 10 to the power of 3 joules. And this is the heat at constant volume. And of course, since work equals 0, the internal change in internal energy is going to be equal to Q. So hence, change in internal energy is going to also be 1.25 times 10 raised to the power of 3 joules. And that is how you answer this question. If you have any questions, please put it in the comment section. If you have any suggestions, also put that in the comment section. If you would want to succeed and get all A's in all your STEM related courses, whether you're in middle school, high school, or college level, make sure you email me at shuhabitutoring@gmail.com. I have packages for personal tutoring as well as group tutoring. If you can afford the personal tutoring, just get yourself a friend or a bunch of your classmates and you guys can um come together and have a session with me. If you would like to put anything in the if you would like to suggest anything, so put it that in the comment section. And if you would like to just book a session to see if we're going to be able to work together and you're going to like me to continue being your tutor, you can also ask for a session and we can work it out. So have a good rest of your day. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.